Section 5.2 is verifying trig identities. So these are statements or equations that we know to be true. You're going to prove that they are in fact true using the fundamental trig identities and your algebra skills. Okay, the nice thing is you know exactly what you're trying to go for, but because you're trying to prove it and it's already true, it's your steps that are important more than the final outcome because we know the outcome. So for example, when it says the cotangent of x times the secant of x is equal to the cosecant of x, when you're proving it, you're going to start with one side and turn it into the other side. It does not matter which side you start with, but you need to write down which side you start with so that your work is clear. Okay, I often start with the more complicated side because it's easier to cancel it into a smaller thing, but you don't have to. You could do it the opposite way and it would still be valid. So there's many ways to do this as long as you are doing mathematically correct steps. Okay, so I'm going to start with the cotangent x, secant x side. You need to rewrite the side you are starting with, so I know. Okay, I know that I'm trying to transform it into cosecant x. Okay, so whichever method we normally simplify is going to be fine. I'm going to rewrite in terms of cosine and sine. Secant is 1 over cosine x. Let's see, so the cosine x will cancel. I'm left with 1 over sine x, which does in fact simplify to cosecant x. Okay, so I did prove what I was trying to prove. I used all the fundamental trig identities to reach the conclusion that the statement told me. Okay, let's go ahead and try example 2. Okay, example 2 says 2 secant squared x equals 1 over 1 minus sine x plus 1 plus sine x. Okay, again, I can start with this side and transform it into this side, or I can start with this side and transform it into this side. I think I'm going to start with the right side this time. Okay, but if during class you would like me to do it the opposite way, I will try to do it the opposite way. Okay, because I'm going to start with the right side, I'm going to rewrite the side I'm starting with to make sure I start with a statement and I end with a statement that I'm trying to prove. Okay, I can see that I'm trying to make 2 secant squared, which is a single expression. So I'm going to go ahead and try to get a common denominator on this thing. Since one is 1 minus sine x, the other is 1 plus sine x. I'm going to make this times 1 plus sine x on the numerator and denominator. And I'm going to multiply this by 1 minus sine x on the numerator and denominator. And I'm just trying to get a common denominator. Okay, I'm going to go ahead and distribute the numerator. So 1 times 1 plus sine x is 1 plus sine x plus 1 minus sine x. Okay, on the denominator, I have 1 plus sine x times 1 minus sine x. Okay, I'm going to go ahead and continue to simplify the numerator. Okay, on the numerator, I can see the sine x minus the sine x will cancel. So 1 plus 1 leaves me with 2 in the numerator. And I am going to go ahead and distribute at the denominator. Sometimes I leave it to see if it'll factor, but because it's 1 plus sine x times 1 minus sine x, I know that's going to turn into 1 minus sine squared x, which is an identity that I can use. Okay, let's see. The 2 is good, and there's a 2 in the final result I'm trying to get anyways, so the 2 is probably going to stay there. Now, 1 minus sine squared x, remember, is a rearrangement of a Pythagorean identity, and that turns into cosine squared x. Okay, 2 over cosine squared x can be rewritten as 2 secant squared x, okay, which was what I was trying to prove. So my proof is done, my verify is done, and I've done what I can. Okay, and again, you could have started on the left side and converted it into the right, and it would still be correct. Okay, I'm going to go ahead and go to example 3. Okay, example 3 says cosecant squared theta minus cotangent squared theta over tangent squared theta, cosecant squared theta equals cosine squared theta. Okay, there is many ways for you to work out this problem. Okay, I'll just go with one example. I'm going to start with the left side just because it looks more complicated. So I'd rather start with something complicated and then hope things will cancel. You don't have to start it this way. You can absolutely do it differently. Cosecant squared theta. Okay, there are so many squares in here. I know that somehow I need to use a Pythagorean identity. So there's a couple ways to do it. Let me see. If you consult with your list of Pythagorean identities, or you derive them again, you'll notice that cosecant squared theta is equal to 1 plus cotangent squared theta. If you know what cosecant squared theta minus cotangent squared theta is, that's also a rearrangement of a Pythagorean identity, and you could rearrange it and use that. Okay, so 1 plus cotangent squared theta minus cotangent squared theta over tangent squared theta cosecant squared theta. Okay, the cotangent squared thetas cancel, which is nice. So I have 1 over tangent squared theta cosecant squared theta. Okay, now you might want to convert to cosine sine now. I don't love the fraction, so I'm going to rewrite this as its reciprocal. 1 over tangent squared theta could be rewritten as cotangent squared theta. Cosecant squared theta, 1 over cosecant squared theta is really sine squared theta. Okay, now I'm going to go ahead and rewrite it. Okay, the sine squared thetas will cancel, and I'm left with cosine squared theta, which is what I was going for. So I have verified it using trig identities and algebra. And again, you can have a different method as long as you're using the trig identities and algebra, then it should be a correct proof. Okay, we're just going to do one more example and then we'll practice some, just because this comes up commonly in calculus. So this one says sine cubed x times cosine to the 4th x equals cosine to the 4th x minus cosine to the 6th x times sine x. And again, I can start with either side. It doesn't make a difference. I'm going to start with the right side because it looks more complicated. If you would prefer to do it the other way, that's fine. And if you would like to see it that way, just remind me during class. Okay, but do write which side you're starting with. Okay, now let me just compare this. The sine x, there was a sine in my final answer. There's sine to the 3rd. There's also a cosine to the 4th in my final answer. Okay, so I'm going to think about that while I work this out. Okay, for these parentheses, they have a common factor. They both have cosine x. They actually both have at least cosine to the 4th x. So I'm going to factor out cosine to the 4th x, which should be nice because I'm going for cosine to the 4th in my answer. Okay, so if I take cosine to the 4th x out of the first term, I'm left with 1 minus, and if I take cosine to the 4th x, I factor it out of cosine to the 6th x, I'm left with cosine to the 2nd x. Okay, and then I still have that sine x hanging out at the end of my expression. So we'll just keep them there. Okay, let's see what I have now. Okay, the cosine to the 4th x is nice because I can see that's what I'm trying to prove. Now 1 minus cosine squared x is a Pythagorean identity. So 1 minus cosine squared x is actually going to be sine squared x. Okay, and then I'm going to bring down the sine x. Okay, let me look at what I'm trying to prove. I'm trying to prove that this is equal to sine to the 3rd x, which it is, times cosine to the 4th x, which it is. Okay, so I proved what I'm trying to prove. And if you had written cosine to the 4th x times sine to the 3rd x, that's fine. It's equivalent and I accept that.